morning, everyone. Today I'm Yukgehnaish from Yukgehnaish Malaysia, and today I would like to share a little bit about phage leads, a tool to predict phage suitability to be used in therapies. Okay, so before moving on to the work. So before moving on to the work, I would like to talk a little bit about the inception of ideas of why we have actually done this too. Now, antibiotic usage is beneficial as long as it is used in, if the usage is actually regulated well. Now, in Malaysia, generally, these three fields are the fields where antibiotics are actually commonly used. Now, the overusage of antibiotics have given rise to the major problem, which is antimicrobial resistant microbes, or AMR microbes. Now, other than medicine, the other two fields, agriculture and agricultural field, the issue is the prophylactic usage of antibiotics, right? So in order to treat a small sample of diseased fishes or livestock, they apply antibiotics to the whole field or the whole fish tanks, right? So now in some countries, the regulation is not as tight, so hence overusage of the antibiotics. Now in Malaysia, in one of the report in 2019, around 265,000 samples were tested, and then out of that, they found that 15% of the Staphylococcus aureus are actually methicillin resistant, and 31.7% of Streptococcus pneumoniae were erythromycin resistant, and so on. Now, this is just for monitoring. They have this monitored, but without any kind of regulation. Now, this is a major issue in countries such as Malaysia. Now, to overcome that, to overcome the AMR issue, the most, there are two approaches that we can look at. The first one is discovering new antimicrobial molecules. However, it may sound simple, but if you look at the timeline below, from 1970s until the current year, there has not been, there is not much new antimicrobial compounds that has been found, which is termed as a discovery void. And the majority of the newer antibiotics are actually just a modification or improvisation of previous classes of antibiotics. Now, the second approach that we can look at is phage therapy, which was discovered before the discovery of penicillin in 1919. It was used for treating dysentery. However, 5 years after the discovery of penicillin, there has been a lot of critical opinion about the usage of phage in treating bacterial infection. However, since 1996, we can actually observe the resurgence of phage therapy. And from that time until this year, a lot of phage therapy studies has been done. And also a lot of products are available, especially in agricultural settings. Now, to actually select a suitable phage for therapeutic reason, we have to look at their life cycle. So they have phages have a choice of going into lytic or temperate life cycle. However, for therapeutic reason, purely lytic phages are actually preferred because they actually kill off the bacteria much more faster. And second thing is, if we use temperate phage for therapy, they might actually integrate exogenous genes into the host. Now, in worst case, they might actually integrate antimicrobial resistant genes or subtoxin genes into the host, which is the bacteria. Now, temperate phages actually are able to, there's two factors that affects the lysogeny of a phage. The first one is it must be able to integrate into the host genome, and integration into the host genome, either it can integrate directly into the chromosome of the host, or it can exist as a separate independent plasmid inside the host. And the second factor is that it has to be able to repress the lytic genes in order for it to maintain the lysogeny inside the host. Now, the lysogeny is actually regulated by integrase or any similar proteins such as serine or tyrosine recombinase. Or in order for it to exist as an independent plasmid, it has to have a chromosome partitioning protein. And in order to repress the lytic genes, it should have a repressors and anti-repressors. Repressors such as CRO and CI repressors. And in order to really select the phages for therapeutic reason, we have to characterize their genome. However, characterizing the phage genome is actually quite hard due to the mosaicity of the phage genome and absence of any universal genes, especially to characterize them according to their phylogeny. And there are a lot of unknown proteins, such as hypothetical proteins. From the data that we have, around 60% of the proteins that we extracted were hypothetical proteins. Now, so in order to actually select a suitable phage for therapy, we have actually came up with a tool which combines the prediction of integrase PAR-A protein immunity repressor, CRO-CI repressor, and anti-repressor using the XTBoost algorithm, which uses the extreme gradient boosting algorithm, and along with the integration of abricate to detect any toxin or antimicrobial genes inside the phage to select the suitable phage for therapy. Now, the first step is in order for the predictor to perform really well, we have to really clean the data that we use for the prediction. Now, we have downloaded more than 9,000 phage genome from the database, and whichever that is before 2018, March of 2018, we use it for training and the testing of the predictor, and after March 2018, we use it for validating the final predictor that we have created. Now, after getting the genome and their proteins, we actually bin them into different bins. This allows us to actually remove any proteins which have less samples in them, right? And also it allows us to remove any unknown proteins from the data set that we are going to use. And then after that, we label it accordingly, according to the predictor that we are creating. For example, integrase, the CRO-CI repressor, and immunity repressor, anti-repressor, and the partitioning protein. Now the protein are actually labeled accordingly. Now, one of the problem when working with a lot of sequences from the database was the misannotation. Now, in order to actually remove misannotated protein, we have done a filtering step where we actually align the proteins, and then we create a network graph according to the bit score, and we use different bit score threshold, 75, 100, and 125, and then we do a step of removal of misfits. So if it is less than 20%, if the misfit is less than 20%, we just remove the particular set of misfits. If it is more than 20%, we remove the whole cluster. So this is how the network graph looks like, and the red are the negatives and the green dots are the positive. Now, if we take a look at this particular cluster, for example, in this small cluster over here, we can see that the positive data is lesser than the negative data. Now, in case if the number of positive here is more than 20%, we will remove this whole cluster from our data. And if it is less than 20%, we will just remove the positive data from here. Now, with that, after cleaning the data accordingly, we move on to the feature extraction. Now, to talk about features, sometimes sequence similarity is not sufficient to actually classify protein. Sometimes proteins with lesser similarity might have the same function or similar function. So in order to actually really extract out the hidden features from the protein data, we actually use the protein features. Now, if you look at, for example, this is just a mock protein. We have to assume that these two proteins have like similar function. If you look at their sequences, we can't actually align them or cluster them together because there is no similarities between them. However, if we actually extract the features out of them, we can observe that for example, the amino acid percentage of D is same and subsequent amino acids are the same. And also isoelectric point of these two proteins will be similar as well as the molecular weight. Now, in our data, we have actually extracted 1,576 features, which consist of peptide frequencies and process domain features and generic protein features such as instability index, Brevy index, and so on. Now, once we have extracted the protein features, we train our predictor using the XGBoost algorithm. Now, right now, we have 5 different data set original, and then the 3 different data set created from the filtering step. The first step to do to train the predictor is to we try to actually minimize the number of features that we use for the final predictor. Now, to do that, what we have done is we do the training in rounds, different rounds, and in the first round we use all the features, and then in the subsequent rounds we actually remove the bottom 50 features from the training. So to observe if the scoring, the metrics are actually good or it is dropping. Now, based on the metrics, we actually select the number of features or the features to be used in the final predictor. Now, then once we have selected the features and also the best data set, we actually train the final predictor using all the data from the data set. Then after that, we actually optimize the prediction threshold. And in the end, we get these 5 predictors for each protein. And this is what it looks like. And the initial number of features is 1,576, and then we reduce the number of features for each round, and then we select the number of features and the best data set based on the MCC value or Matthews correlation coefficient scores, which provides much more better metrics for imbalanced classes. And these are the features, that number of features and the data set that we have actually used in the final predictor. And the MCC score was quite high for all, it's more than 80% for all the predictor. And the number of features is around 129 to 350. And these are the features, some of the features that we have used according, it is plotted according to their importance in terms of classifying our protein. And you can see that some of the features are used on BEAM. It is able to differentiate only one type of protein, and some features are actually important to predict all different proteins. Now, this is the amino acid percentage, and these are the generic protein features, for example, the instability index, isoelectric points, and entropy of the proteins. Now, after we have selected the best features and also the best data set to predict for generating the predictor, we created the final predictor, and with that we validated the predictor using the validation data set. And we can see that the MCC score is quite good for the integrase, anti-repressor, immunity repressor, and CRO-CI repressor. However, for chromosomal partitioning protein A, the MCC score was a bit lower. This might be due to the low number of positive data in the validation data set. Out of all the proteins, partitioning protein A was the least number in terms of the number of sequences. And the problem with CRO-CI repressor is that a lot of the annotation were ambiguously annotated. For example, it might be CRO-CI repressor, or they just annotate it as transcriptional regulators. So now, once we have actually created the final predictor, and using the best features, we actually cross-validated them. So we used a tenfold cross-validation. This was done to actually determine if our predictor is actually able to predict new samples. So what we do is we have actually done this in 2 ways. We used a random tenfold cross-validation and CD-HIT tenfold cross-validation. In random tenfold cross-validation, we actually bin our data into 10 bins randomly, and then we cross-validate them. And in the CD hit 10-fold cross-validation, what we have done is we cluster the protein with 0.6% similarity, and then we bin them into 10 different bins, but we make sure that there are no cross-clusters proteins in each of the bin. So this is the result for the random 10-fold cross-validation. So in random cross-validation, the scores are quite okay. So everything is more than 80%. And which means that if our predictor is able to learn to predict any unincluded data set in the training. And in the CD hit 10-fold cross-validation, the scores for partitioning protein A and CRO repressor is quite low. What this indicates is that the sequence similarities actually plays a role in the classification of the proteins. So, and also it is important to note that we have to include as many data as possible for our predictor to actually learn to predict properly, to predict with high accuracy. And after that, after the creation of the final predictor, what we have done is we actually collected the data from the Fudge lifestyle data set by Maverick and Headful, and we test them using our phage leads predictor to test whether we are able to predict their life cycle, either it is lytic or temperate phages. Now in the data set, they had 240 temperate phages and 183 lytic phages. And using the predictor, using the phage lead predictor, we have able to achieve the accuracy of 96% and the MCC score of 92.8% with a false positive of 1.42 and false negative rate of 2.12%. Now, and these are the number of markers that is in the phages that was predicted as temperate. So we can see that the 16% of the temperate phages had only one of the marker or one of the protein that our predictor predicted, and 59% of the temperate phages actually contained a combination of two markers, and 20% of the phages contain three markers, and only 5% of the phages has a combination of four markers. And the difference of the phage lead predictor is that there are actually two other lifestyle predictor available, such as FACS and backflip. Now, in our predictor, we actually did not use any kind of similarity algorithm or any domain similarity algorithms. And information of the phage lifestyle is not included in the training process of phage leads. And also, we did not use the whole proteome of the phages. Now, the major difference is that the number of data that we have used in our training, for example, in backflip and FACS, 977 genomes were used, which generated around 42,000 proteins. And in our predictor, we have actually used 7,689 genomes with more than 180,000 proteins. Now, why is it important to use a large data? Is because we are most likely to able to predict the underrepresented phages in the phage data set. For example, marine phages. So by using phage leads, we will be able to actually predict underrepresented phages. And also, we don't have to look at the whole proteomics of the phage to identify their lifestyle. The presence of these 5 markers that we have used is actually sufficient to determine their ability to switch to the temperate cycle. And then also another thing is we can use the predictor to actually just test the presence of integrase or repressor, immunity repressor, partitioning protein, and also we can actually use them to predict the presence of these proteins individually. And So the next step of our work will be to incorporate with the abricate toxin and the antimicrobial resistant gene finder in the final version. And also another recent discovery is that from AlphaFold protein folding tool, they showed the existence of some proteins which are not similar at all in terms of their sequence, but they have very similar structures, which may indicate that it has the same functionality. So it is a great method for classifying proteins. And also we can use that to increase our data set, whereas we can actually use the AlphaFold predictor, AlphaFold protein structure predictor to actually predict similar proteins as structurally similar proteins. And we can use that to actually classify unknown protein, especially hypothetical proteins in phage genomes. Thank you for listening. And the phage lead is actually available in phageleaks.tk. It is a part of Phage Compass consortium. So it is relatively new. It has just been hosted, so we can try to use it. So that is all from me. Thank you.